Hi, welcome to Gravity Part 2. In this part, we're going to look at the relationship of force of gravity and centripetal force. This obviously applies to uh, one body orbiting another body. When this happens, the gravitational force, or the force of gravity, is exactly equal to the centripetal force. And as you can see on your screen, the force of gravity over here on the left is equal to the centripetal force, which is over here on the right. Universal gravitational constant, the body doing the orbiting, the body being orbited, the radius, the distance between the two bodies, m1 and m2. m1 again, the body doing the orbiting, 4 and pi are constants. R is the radius of the orbit, t squared is the period of the orbit. Now obviously that we have m1 in both sides of the equation, so we can take that out and we have this relationship simplified, and as you see, the body doing the orbiting doesn't come into play. I'm going to do an example here, and what we're going to do is find the radius of a body in a geostationary orbit. What that means, if here's the Earth and here's a satellite orbiting it, that satellite always stays the same over the same spot on the Earth. So its period of rotation is equal to the period of rotation of the Earth. And just to remind you, the period of rotation of the Earth is 24 hours. Not exactly 24, I know that, but I'm not interested in the decimal places. I'm interested in showing you how this problem is done. And that translates into 8.64 times 10 to the 4th seconds. So if we go ahead and do our arithmetic here, start with our equation, we get that the universal constant times the mass of the Earth over r squared is equal to 4 pi squared times the radius of the orbit over t squared. G is 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared times the mass of the Earth, 5.97 times 10 to the 24 kilograms over the radius squared, equal to 4 pi, 3.14 for our purposes, r over t squared, and t is 8.64 times 10 to the 4 seconds, and so you have to square that. Solving for r, we do the arithmetic. You see r times this r is r cubed. This comes to the numerator, these go into the denominator. It's going to give us an equation to solve for, equal to 6.67 times 10 to the minus 11 Newton meters square over kilograms square times the mass of the Earth, 5.97 times 10 to the 24 kilograms times the period squared, 8.64 times 10 to the 4th seconds squared, and in the denominator we have a friend 4, 3.14 squared. I'm sure that you're all competent enough to use a calculator. You're going to get r cubed is equal to 7.54 times 10 to the 24th meters cubed. Take the cube root of both sides, you get 4.22 times 10 to the 7th meters, which is approximately 25,000 miles. Now, how do we work out the units? Remember that 1 Newton is 1 kilogram meter per second squared. So for G, for example, when you have G, we have Newton meters squared per kilogram squared. Well, substitute in this kilogram meters squared divided by seconds squared kilogram, I forgot the squared here, kilograms squared, which gives us meters cubed, kilograms divided by seconds squared, kilograms squared. So when you plug this into our equation, we get G, which is, or these units, meters cubed, kilograms, seconds squared, kilograms squared, times the mass of the planet Earth, which is given in kilograms, and times seconds squared. Seconds squared nicely reduce, kilogram squared, and we end up with meters cubed. So when we take the square root, we end up with meters. Hope this helped. Please feel free to leave a comment. Let me know what's clear or not clear. You want to see more examples, anything that would enhance this. Thanks.